So today we're going to take what we've seen in sinusoidal functions and kind of relate it to more general functions, the polynomial functions specifically, but understand that whatever we've done we can do on any function at all. So kind of a lengthy bit of a note here, but sort of the key factors. Sinusoidal functions, we know amplitude, we know period, we know phase shift, we know vertical shift. So we understand what A, K, D, and C represent. When we move to polynomial functions and have the exact same form, so here we have the same form just with a polynomial, A in front, K, D, and C, what happens is essentially the same thing. So originally we were saying that A determined the amplitude, so essentially the stretch of the sinusoidal. Well, there's no amplitude now with polynomials, but basically the rest of it's the same idea. So we determine how many times higher or lower any given point is than it was in the base function. Okay, so if you think about your sine curve, at the maximum point you had a 1. If the amplitude is 4, that 1 got pulled up to a 4. The minimum point was a -1, it got pulled down to a -4 prior to any shifting that occurred at least. Now when we look at K, this is the one part that maybe doesn't translate perfectly from sinusoidals to other functions. The original read, K determines the period of the graph, how wide each cycle is. Obviously with a polynomial function we don't have a cycle. But basically what we said before was if K was 3, we had 3 full graphs in the width that originally one graph would be. So that means that we've compressed our graph to be about 1/3 of the size. And so that's the same idea again here. Each point will be only 1/3 of the way as far as it was. Or, if you think about the graph, we could fit 3 of the original graphs in the same amount of space. So reworded here determines how wide the one cycle we have is compared to the base function. We'll see that a little bit better when we do the example. And the shifting, of course, is pretty straightforward. Every point's going to shift left and right, up and down, exactly as it did before. So sort of with the polynomial functions, we might want to think about individual points a little bit more than the cycles, because of course we don't have the cycles again. And then negative values A and K just flip our graph around the X and Y axes. Okay, so if we look at an example, and I'll bring it up in Desmos in just a second. So we're thinking about this specific example. So essentially the -2 says to double the height and then make them negative. Okay, so whatever this works out to be, we're going to multiply by -2. So these are the y values up to a certain point. We multiply them by -2. They become twice as large, in quotes, absolute value wise, and then the negative, of course, flips. -4 says we should be able to fit 4 of our graphs horizontally in the same amount of space, so our x values are 1/4 of what they were. Okay, so if we look at that on a graph here, I've got the graph x cubed to start. My first step would be to look at the 4 specifically, just because that's the order I've chosen to do them in. Usually we do work left to right for discussion purposes. This is just the way I broke it down. And so if we look at any given point here, let's move this up. At the point here, y is 5. So my 2 points are these values. And the number 4, of course, is what we're interested in. So an x value here of 0.4, a little bit more obviously, multiply that by 4, we get 1.6. So this point is 1/4 as far out as this one was. Let's see if we can find one that's a little bit nicer here. I guess there's a nice one right down there. At x value of 1/4, we get the equivalent. The old value was x value of 1. So this is my original point. It's now 1/4 as far in, which suggests that we can get, if we had duplicates of this, we could get 4 of them in the same amount of space. And is there another nice one up here somewhere? Okay, and so there's of course a nice one as well at 0.5x here. This is where we were originally at 2. Obviously that's 4 times as wide. And so now, no surprise here, I don't suppose. The negative is simply taking my 4 graph here and flipping it over. We won't really have to worry about that one too much. And then if we look at the negative 2 here, we're saying take whatever we had. So take whatever we had here, make it negative, so flip it back to the other side. But the 2 specifically is just taking any given point, and I wonder if I can do this way. And double its location. So if we look at this, we have 0.5. At 0.5 we have a value of 8. Up here at 0.5 we have a value of 16. So the point here has been stretched up to the point double the height, again because of the number 2. And then the second example basically goes through the same thing, but with the, sort of in a general sense, the n value, it says, is unimportant. So whether this is a square, a cube, a fifth power, or anything else, all these other numbers do is move our graph around, stretch it, compress it, so stretch it vertically, compress it horizontally, and then shift it to the right and shift it up. So if we look over here now, I've got x squared graphed. And again, the exponent doesn't matter when we're looking at these transformations. Essentially, whatever the original graph is, these values will affect it the same way. Again, the 3 here is going to compress horizontally. And so if we look at the first step, we've got this horizontal compression. And at any given point here, I've got the y value 5 is at 0.7 for an x value. The original value is 2.2. Okay, so 0.7 times 3 is 2.1. Obviously, it's a little bit beyond that, so you can get the idea that it is 3 times as far out there. If we continue up, find a nice value here. We've got 1.05 and just over 3 here, so 3 times again. Okay. And then we can continue with the same process. The 4 here. Okay, so I changed my axes a bit so we can see these graphs a little bit better. The purple is the 3x quantity squared, and the red graph is the 4 times that. So if we look at any individual value here, it's going to let me do this. And we've got 0.5 here at 2.25. This one is at 9. 2.25 times 4 is 9. So you can see that that point is 4 times as high. So again, this graph, the purple graph, has been stretched up now by the 4 so that each point is 4 times what it was. And then the last step, zoom it in here a bit if I can, or zoom it out a bit I guess. You can see that what was our 0, 0 point has shifted over 2 and up 1 to be at 2, 1, and so each of the points has shifted to the right for this -2 and up 1 for the 1. Okay, and then again, last comment again was the n does not really matter in this question. If I'd used a 4th power or a 5th power, the graphs would look the same but shifted in each case. So that's the information. You're going to apply that to some questions for the next couple of days, and hopefully it'll start to look a bit more clear as you do it yourself.